Hello, my name is Rihanna Howard.
And my name is Larry Webster.
This is our presentation on the full design process of reaching the goal of creating a better electric car jack.
Some backstory. During a snowstorm in January, my wife's car developed a flat tire. The next morning, I had to go out and attempt to jack up her car and change the tire. The jack that came standard with the car barely fit underneath, and then I had to lay on the cold, wet ground to place the jack and start lifting it. The crank that came with the jack was too big, so I had to use a crescent wrench to attempt to get the car lifted up high enough to then have enough clearance to rotate the crank. After an hour and a half, I had the tire changed, but I was soaked. Most of my knuckles hurt from slipping and hitting the undercarriage of the car, and I decided then and there an electric car jack would have made everything so much simpler.
The first step was to evaluate the needs of the customer. We began by searching for similar products on Amazon and reading the reviews of the customers that gave positive feedback and the ones that gave negative feedback. The positive reviews gave comments such as, "The jack has a metal base, giving it weight and stability. It was easy to use. The simple operation was great. It was very heavy duty and nicely compact." The negative reviews included comments such as, "There was a loss of power due to jack blowing a fuse and there is no manual wind down. The frame bent while operating. My car has to be on to use this. It is made from sheet metal. And the top plate is too small, so my car fell off." From these comments, we determined the primary needs of the customer in order of importance. The first need is that the jack needs to be made from good and strong materials, meaning that the metal won't be likely to bend or buckle and the electric motor is not made from plastic. The second need is that the jack is easy to use, meaning that the user doesn't need to operate it manually, and the motor allows for incremental adjustments. The third need is that it can still be used if the car has no power, meaning the jack is not dependent on power from the car, and if there is a loss of power, it can be manually raised or lowered. The fourth need is for the jack to be compact yet strong, meaning that it can fit with the spare tire in the trunk of a car and can be able to lift heavier vehicles. The fifth need is for the jack to be quick, meaning that it can lift a car in approximately 1 minute and allows for the quick reversing of a direction.
After determining the most important requirements from a customer perspective, we were able to determine the engineering requirements that would be necessary to develop a working car jack. These requirements would become our biggest focus. After comparing the engineering requirements with our customer requirements, we determined the importance of each of these engineering requirements. Most important were the materials used, primarily to ensure stability and safety. Then, things like the extension type and weight capacity. The motor capabilities were important, but not as important as the safety and sturdiness of the jack. The least important aspects were the overall weight and the overall dimensions of the jack itself.
To generate design ideas, we used external and internal methods. The external methods we used were benchmarking, experts, and existing patents. The internal methods we used were the gallery method, functional decomposition, and biomimicry. While many sources were used to find different attributes for our concept, functional decomposition and browsing through existing patents were most helpful for generating ideas. This shows a small handful of ideas that went into developing a viable product. Some designs that were considered included things such as a telescoping car jack, a scissor lift, a hand crank, a locking system, a large inflatable pillow inspired by a pufferfish, lead screws with a pulley, and many others. While many different sources were used for inspiration, the concepts shown here are the ones that were most important for the final design consideration.
Narrowing down the engineering requirements into design criteria, we took 6 of the concepts that we determined were most achievable. After determining the weight of each design criterion and determining how likely each concept was to meet the design criteria, we determined that our most favorable design was a scissor jack with parallel lead screws that were rotating with a single motor.
This shows our preliminary sketch for the design. There would be a top platform, 3 scissors with 2 lead screws, a pulley between the lead screws, a motor, and a textured base to help keep it from sliding. However, after some outside input from people much smarter than us, we realized that it would be way too big of a task to solve how to make a pulley between 2 moving objects work with the time that we had, so this design was modified into something more attainable. The next option was our second highest scoring design, a single lead screw jack with the addition of a removable motor. This new design will not be able to lift something as high, and it has a design very similar to other existing designs. The main difference will be that this jack will have a motor that can be removed if necessary, or if the user has a fear of motors, and be operated manually instead. The next step was to choose what material the main part of the jack would consist of. We used CES EduPack to compare aspects of materials that were important to the design. In this case, it was having high compressive strength and a lower density of material. We picked a few materials that incorporated these two characteristics. These materials were tungsten alloy, tool steel, low carbon steel, chromium alloy, and molybdenum alloy. Based on the estimated total weight and cost of the metal, we decided to use low carbon steel for the development of the jack. Low carbon steel would give us a high compressive strength without being too heavy for the average person to lift.
In order to determine the motor we would need to operate the up and down motion, we had to look at the load that would be applied to our single lead screw and the total torque required for a motor to turn it. Using equations from a number of scientific papers written on the subject, we determined that if the jack is forced to lift 1,500 pounds, which is a half of a brand new Toyota Corolla, the motor would need approximately 23.64 pound-inches of torque. We were able to find a motor that would offer 22.11 pounds of torque at 30 RPM. While this is lower than the torque mentioned in the last slide, the 1,500 pounds was an over-approximation, which means this motor should be more than enough to meet our requirements. In order to differentiate our car jack from others, we decided to create a removable system for the motor. The trunnion with the head of the lead screw would be made with 4 metal prongs, and the motor would have a set of prongs added to it to fit into the trunnion. This would allow the lead screw to fit perfectly into the custom bit, and the torque of the motor would be able to turn the screw rather than breaking the connecting prongs. This allows for the motor to be taken in and out depending on if the motor has supplied power to it or not. The final model is a pretty standard single lead screw scissor jack. However, the addition of the removable motor sets it apart from other similar models already in the market. Here is a list of our material needs. We need enough steel to be machined into all of our parts, but we will order excess for any unseen issues that may arise. We need 4 connecting screws and 4 hex nuts to fit on them to connect the base and load bearing plates with the arms. Then we need a lead screw in the motor. For the entire jack, the price should be around $160 to create a prototype.
Our next step is to build a working prototype with all the information we currently have. After creating this prototype, we will perform numerous tests to determine failure points and work to improve each point, as well as determine where we have too much material. These points can be cut down while still ensuring structural integrity to save on material costs. Once we have a good prototype, we will market the product to the public, receive feedback, and repeat the process accordingly. Thank you for watching our video. And it should be noted that this car jack is much improved from the 450-pound car jack we started with.
With engineering students like you, we thank you.